The following theorem provides us with 3 useful facts related to invertible matrices. So our first useful fact is that if matrix A is an invertible matrix, then the inverse of matrix A is invertible, and the following property holds true. And that's that the inverse of the inverse is equal to matrix A. And we'll look at the corresponding proof to this useful fact momentarily. The second useful fact about invertible matrices is that if matrix A and matrix B are n by n invertible matrices, then so is their product, matrix A times matrix B. And the inverse of matrix A times matrix B is the product of the inverses of A and B in the reverse order. So what is this saying? Well, this is saying that the inverse of the product matrix A times matrix B is equal to the product of the inverse of matrix B multiplied by the inverse of matrix A. And again, we'll look at the corresponding proof to this useful fact momentarily. But first, we have one more useful fact. Number 3. If matrix A is an invertible matrix, then so is the transpose of matrix A. And the inverse of the transpose of matrix A is the transpose of the inverse of matrix A. So in other words, that's saying that the inverse of the transpose of matrix A is equal to the transpose of the inverse of matrix A. So now that we have seen these 3 useful facts, let's go ahead and verify that they in fact hold true. So the first property of this theorem tells us that if matrix A is invertible, then the inverse of matrix A is also invertible, and the inverse of matrix A is equal to matrix A. So let's verify that this is in fact holding true. So to begin, we want to let A be some n by n invertible matrix. Now, what exactly is it that we want to show? Well, we want to show that the inverse of matrix A is also invertible. So to show that the inverse of matrix A is invertible, we need to show 2 things. We need to show that the inverse of matrix A multiplied by the inverse of matrix A is that n by n identity matrix. And we also need to show that the reverse order holds true. Now, we've got a lot of inverses going on here. So to simplify things, let's go ahead and we'll let matrix C be equal to the inverse of matrix A, just to make things a little bit easier to understand. Now, keep in mind that we already sort of know that matrix C must be equal to matrix A. And that's because matrix A is invertible. And inverses, as we know, have unique solutions. But we still need to go through and verify this formally. So here we go. Case 1. Let's suppose that the inverse of matrix A multiplied by matrix C is equal to that n by n identity matrix. Now we want to again confirm that matrix C is in fact A, making the inverse of A invertible. So how are we going to do that? Well, let's start by left-hand multiplying this equation by matrix A. So if we do that, we have matrix A multiplied by the inverse of A times matrix C, which is equal to matrix A multiplied by the n by n identity matrix. Now, by properties of matrices, we can see on the left-hand side that we can reorder this. So we have matrix A multiplied by the inverse of matrix A multiplied by matrix C. And now on the right-hand side, we know that a matrix times the identity matrix is just that matrix. Now again, by properties of matrices, and since matrix A is invertible, we know that A multiplied by the inverse of A is just that n by n identity matrix. So we have the n by n identity matrix multiplied by matrix C equals matrix A, which is the same thing as saying matrix C is equal to matrix A. Woohoo! So our first case is all set, and now we want to do the same thing but going in the reverse order. So for case 2, we want to suppose that this matrix C multiplied by the inverse of matrix A is equal to the n by n identity matrix. And again, our goal is to show that this matrix C is equal to matrix A to allow the inverse of A to be invertible. So how are we going to do that? Well, let's begin here by right-hand multiplying this equation by matrix A. So here we have the product matrix C times the inverse of matrix A multiplied by matrix A, which is equal to the n by n identity matrix multiplied by matrix A. And just like in case 1, we can reorder the terms on the left-hand side. So by properties of matrices, we now have C times the product of the inverse of matrix A multiplied by matrix A. And we know that the identity matrix multiplied by a matrix is just that matrix. Now, since matrix A is invertible, we know that the left-hand side becomes C times that n by n identity matrix, which is still equal to matrix A. And matrix C times the n by n identity matrix is simply equal to matrix C. And we've shown again that matrix C is equal to matrix A. Woohoo! And we're ready to state our final conclusions. So we can say that, therefore, since we let the inverse of matrix A be matrix C, and since we have shown that matrix C is in fact matrix A, then the inverse of matrix A must be equal to matrix A, and thus the inverse of A is invertible. And so this completes the proof of this property. So the second property of this theorem says that if matrix A and matrix B are n by n invertible matrices, then their product, matrix A times matrix B, is invertible, and the inverse of the product, A times B, is equal to the product, the inverse of matrix B, multiplied by the inverse of matrix A. So, to get us started, we simply want to let matrix A and matrix B be n by n invertible matrices. So, what exactly is it that we want to show? Well, we want to show that matrix A times matrix B is invertible. So we need to show, again, two things. We need to show that matrix A times matrix B multiplied by the inverse of this product is the n by n identity matrix. And we also need to show that the reverse holds true. So we have two cases again. Here we go. So for case 1, we want to show that matrix A times matrix B multiplied by the inverse of this product is equal to the n by n identity matrix. So to get us started here, let's suppose that the inverse of matrix A times matrix B is in fact equal to the product of the inverse of matrix B multiplied by the inverse of matrix A. And we're going to use this equation to help us attain the desired result. So, looking at that desired result here, how can we use this equation to attain what we need? Well, let's start by left-hand multiplying the equation by the product AB. So here we go. We have on the left, we're multiplying by the product AB, and this is multiplied by the inverse of this product. And we have on the right-hand side, again, we are left-hand multiplying by the product AB, and this is multiplied by the inverse of matrix B, multiplied by the inverse of matrix A. Now, let's leave the left-hand side alone and think about what we can do on the right-hand side. Well, by properties of matrices, by matrix multiplication, we can reorder this right-hand side so that we have matrix A multiplied by matrix B times the inverse of matrix B multiplied by the inverse of matrix A. And now, since matrix B is invertible, we know that this is equal to matrix A times that n by n identity matrix multiplied by the inverse of A. Or in other words, this is simply matrix A times the inverse of A. And hey, since matrix A is invertible, that's equal to the n by n identity matrix, which is exactly what we need. Woohoo! And so we can make the conclusion that therefore, the matrix defined by the product AB multiplied by the inverse of this product is equal to the n by n identity matrix. So case 1 is done, and we now need to go through and look at case number 2 using a similar method. So here we go. Case 2, this time we want to show that the inverse of the product matrix A times matrix B multiplied by the product AB is also equal to the n by n identity matrix. So to begin, again, let's suppose that the inverse of matrix A times matrix B is equal to the product of the inverse of B times the inverse of matrix A. So using this equation, let's now go ahead and right-hand multiply by the product AB. Again, we know to right-hand multiply because of what we're trying to show. So we now have the inverse of the product AB multiplied by the product AB, and this is equal to the product of the inverse of matrix B multiplied by the inverse of matrix A multiplied by the product AB. Now, by properties of matrices, or matrix multiplication, we can reorder this right-hand side so that we have the inverse of matrix B multiplied by the inverse of matrix A times matrix A multiplied by matrix B. And since we know that matrix A is invertible, this is equal to the inverse of matrix B multiplied by the n by n identity matrix multiplied by matrix B, or in other words, the inverse of matrix B multiplied by matrix B. And now, since matrix B is also invertible, this is equal to the n by n identity matrix, which is what we wanted to show. Woohoo! And we're ready to state our final conclusions here. So in regards to case 2, what have we shown? Well, therefore, the inverse of the product A times B multiplied by the product AB is equal to the n by n identity matrix. And we're ready for the finale. We can say that therefore, since both cases hold true, we have officially confirmed that the product matrix A times matrix B is invertible. Hooray! This completes the proof of property number 2. And last but certainly not least, property number 3. And this property says that if A is an n by n invertible matrix, then the transpose of matrix A is also an invertible matrix, and that the inverse of the transpose of A is equal to the transpose of the inverse of A. So, to begin, let's let A be an n by n invertible matrix. Now, what is it that we want to show? Well, we want to show that the transpose of A is also invertible. So in other words, we need to show those two conditions, that the transpose of A multiplied by the inverse of the transpose of A is that n by n identity matrix, and that the reverse holds true as well. So here we go. We have two cases. So case number 1. Let's show that the transpose of matrix A multiplied by the inverse of the transpose of matrix A is equal to that n by n identity matrix. And keep in mind, we want to incorporate in this other condition. So let's suppose that that holds true. So we want to suppose that the inverse of the transpose of matrix A is equal to the transpose of the inverse of matrix A. Now, we're going to use this equation to help us attain the desired result. So, keeping that desired result in mind, let's start here by left-hand multiplying by A transpose. So we have the transpose of matrix A multiplied by the inverse of the transpose of A, and this is now equal to the transpose of matrix A multiplied by the transpose of the inverse of matrix A. So we're going to leave the left-hand side alone, and we want to manipulate the right-hand side to attain that identity matrix. Now, the right-hand side can be rewritten using the properties of the transpose. So we can rewrite this as the transpose of the inverse of matrix A multiplied by matrix A. And now, since matrix A is invertible, we know that this is equivalent to the transpose of the n by n identity matrix, which is just equal to the identity matrix. That n by n identity matrix, which is exactly what we need. Woohoo! And so we can conclude that, therefore, the transpose matrix A multiplied by the inverse of the transpose of matrix A is the n by n identity matrix. And case 1 is done. But we still need to go ahead and use this same method to show that case 2 holds true. So here we go, case 2. Here we want to show the reverse. Or in other words, we want to show that the inverse of the transpose of matrix A multiplied by the transpose of matrix A is the n by n identity matrix. So again, to start here, let's suppose that the inverse of the transpose of matrix A is equal to the transpose of the inverse of matrix A. And now again, keeping that desired result in mind, let's go ahead and right-hand multiply by the transpose of matrix A. So this is going to leave us with the inverse of the transpose of matrix A multiplied by the transpose of matrix A is equal to the transpose of the inverse of matrix A multiplied by the transpose of matrix A. Now again, we'll leave the left-hand side as it is, and we can rewrite the right-hand side by the properties of the transpose. So this is equal to the product matrix A multiplied by the inverse of matrix A transpose. And since matrix A is invertible, we have the transpose of the n by n identity matrix, which again is just the n by n identity matrix, and exactly what we need. Woohoo! And so we can say that, therefore, the inverse of A transpose multiplied by A transpose is the n by n identity matrix. And we're ready to state our very final conclusion. We can say that, therefore, since both cases hold true, we have officially shown that the transpose of matrix A is invertible. And this completes the proof of property number 3 and this theorem.